Good morning to all. Today we are going to learn about Schrodinger equations. Basically, it is a reduction of Schrodinger equation for two particles to one particle system. So this is the presentation outline of today's talk. First, we'll write Schrodinger equation for a particle. Now, it is an eigenvalue equation for a single particle is written like this: h cross square by 2m delta square psi plus e minus v of r into psi equals 0. Now, nucleus is more or less spherically symmetric. That's why the wave function what we use will be a spherical wave function. So, wave function expressed in spherical coordinates. Now, it can be expressed like psi of r theta phi equals r of r into y theta phi. R of r is function of only radial coordinate. Y of theta phi is function of only angular coordinate. It's called as spherical harmonics. Now, if potential is function of only radial coordinate, then we can use variable separable method and we can remove the dependency of angular contribution. So, writing radial part of this Schrodinger wave equation will be like this. So, the equation 1 what is written will now become h cross square by 2m delta square r of r plus e minus v of r minus l into l plus 1 by r square into r of r equals 0. Okay. Note this, we have extra terms here, l by l into l plus 1 by r square came entirely because of the separation of angular part of the wave function from the equation 1. L therefore is called as angular momentum quantum number. Now this particular equation now has two potential V of r and L into L plus 1 by r square also acts as a potential. It's called as centrifugal potential. So it will be in a direction opposite to that of the first potential V of r. So it's called barrier because it will be in the zeros direction. Now this equation is valid for one particle system. Now let us look at if we plot a graph of total potential which is written here, V of r plus L into L plus 1 by r square. So that's the total potential that is present in the Schrodinger wave equation. Now we can plot a graph of potential for different values of r. So the curve will look like this. So this plot contains three curves. First one is actually V of r we have plotted here as a Coulomb potential which is proportional to minus k by r. So where actually k can take any value here. So here in this plot actually k value used is 15. And that curve is plotted in blue dotted line which goes like that. Okay. Then the centrifugal barrier is plotted in a red dashed line which is in the positive direction. Sum of these two potential is also plotted, that is in solid line, brown color solid line. So all these three curves shown here. So this is a special case in which this plot k is actually plotted with k equals 15 and L is with 3. So this is actually a plot of potential. Now let us write Schrodinger equation for two particles. So in nature there are plenty of examples of two particle system. Few of them include hydrogen atom and deuteron. Hydrogen atom contains two particles, nucleus and electron, proton and electron. A deuteron is a nucleus of heavy hydrogen, one isotope of the hydrogen, which contains only two particles. These two systems exist in bound state. There are also many other examples which exist in free state and those causing either scattering or collision. So these are a few examples in which actually two particle system is written. Now our task is to write Schrödinger equation for such two particle system. Now let m1 and m2 be the masses of the two particles with position coordinates r1 r2 as shown in this diagram. Now the interaction potential acting between the two particles will be equal to V of r1 minus r2. So that's position vectors. Actually, how these two particles move relative to each other decides the potential interaction potential between the two particles. So with this background, we can write Schrödinger equation for two particles, an eigenvalue equation, and that will appear like this. This is similar to equation 1, but it is now written for two particles. Minus h cross square by 2m1 delta 1 square minus h cross square 2m2 delta 2 square plus v of r1 minus r2 into psi of r1 r2 equals ei into psi of r1 r2. This is the equation. The important thing is the potential is not now actually simple function. It is now actually function of two coordinates v r1 minus r2. Additionally, the wave function psi of r1 r2 is also function of two different coordinates r1 and r2. In the equation 2, delta 1 square, delta 2 square actually second order differential operators, Laplace square operators with respect to particle 1 and 2. What is actually stopping us from proceeding from this position is actually that in this case the wave function psi of r1 r2 cannot be written as a product of independent wave functions phi1 of phi of r1 into phi of r2. So it cannot be written like this. This is an hindrance and it stops us to go further analysis. So we have to overcome from this hindrance. So how to go ahead from here onwards? The technique people used is actually to change from lab frame of reference to center of mass frame of reference with coordinates r and rho as shown in the adjacent diagram. So this diagram shows the two vectors r and rho. So r is actually vector distance, separation distance between the two particles m1 and m2. This is a vector quantity, and this rho is actually center of mass coordinate, which gives the location of the center of mass of the two particles. So therefore, the relative coordinate r is simply written as r. Actually, it is r of 1, 2. So for now onwards, we will use only vector r. R is defined as r1 minus r2, calling it as equation 3. And from the definition of the center of mass coordinate, we can write the expression for center of mass coordinate r as m into rho equals m1 r1 plus m2 r2, where capital M is total mass of the system, which is sum of m1 plus m2. Now when we write like this, the wave function now actually can be written as psi of r comma rho. So we are changing from r1 r2 to r comma rho. Now when we write wave function like that, it is possible that the wave function can be separable, like product of phi of r into phi of rho. So this is an advantage which is useful for us to proceed further for analysis. Now actually the task is also to transform collectively the operators delta 1 of r1 and delta 2 of r2 to delta r of r and delta rho of rho. Now this can be done using equation 3 and 4. What is delta 1 of r? So delta 1, the operator which is acting on the wave function psi of r comma rho, is nothing but simply a partial derivative of psi with respect to vector r1. This is a vector r1. It's not simple coordinate. It's a vector r1. Now psi is function of both r and rho. Therefore, you get the partial derivative of the two variables. When you do like that, you get a product like this. Dou psi by dou r into dou r by dou vector r1 plus dou psi by dou vector r vector rho correction into delta rho by delta r1. Now in this actually delta r by r1 is determined from equation 3. Delta rho by delta r1 is determined from equation 4. So you get the values of those partial derivatives from equation 3 and 4. And delta psi by delta r can be denoted as delta rho. This quantity delta psi by delta r can be written as delta r, and similarly delta psi by delta rho is written as delta rho. So with these notations you will get delta 1 of psi of r comma rho gives us to delta r plus m1 by m capital M into delta rho into psi of r comma rho. Now from this you can separate out the operators delta 1 expressed in terms of delta r and delta rho. So you get this particular expression. Delta 1 is written as delta 1 delta r plus m1 by capital M into delta rho. I'm calling it as equation 6. So exactly on similar lines you can also obtain expression for the operator delta 2 by using equation 3, and you get this particular part. So operator delta 2 is equal to the quantities which are in the square bracket of RHS of equation 7, which is equal to minus delta r plus m2 by m into delta rho. So negative sign is because of the negative sign associated with r2 in equation 3. So we have now determined the values of the two operators delta 1 and delta 2. Remember these two because we will be using that. Now what we do, we consider delta 1 square by m1 plus delta 2 square by m2. Substituting the values of delta 1 and delta 2 from equation 6 and 7 shown in the previous slide, you get this particular part 1 by m1 into some such things. So you can expand this using a plus or minus b whole square, and there is also factor 1 by m1 for the first term, 1 by m2 for the second term. If you square and add the two parts, you get a square plus b square plus 2ab for the first part, a square plus b square minus 2ab for the second part, plus 2ab minus 2ab, they will get cancelled. So the resultant thing is you get an expressions like this: 1 by m1 delta r square plus m1 by capital M square into delta r square plus 1 by m2 delta r square plus m2 by m square into delta rho square. Now you can regroup these terms, the terms containing only delta r and the terms containing only delta rho. When you do like that, you get this quantity that's equal to delta r square by mu plus delta rho square by capital M, where mu is actually reduced mass, is defined as m1 m2 divided by m1 plus m2, and capital M is the total mass of the system. So with this equation 8 you can substitute this transformation, and also along with the equivalent wave function and the potential function in equation 2, which is for equation for two particle system. This in CM system, it becomes minus h cross square by 2 into delta r square by mu plus delta rho square by capital M plus v of r into psi of r comma rho. Note that this potential is now actually a function of a single coordinate, relative coordinate. Also, this energy eigenvalue is a scalar additive term. So it can be written as ER plus E rho. ER corresponds to energy associated with the relative coordinate, and E rho is the energy associated with the center of mass coordinate. and substituting the values of for wave functions and results in the equation 2, it leads to this particular equation 10, and which is regrouped again, and divide this equation 10 by the product phi of r into phi of rho, and separate in the terms only containing phi of r and phi of rho. You get two equations. One equation is minus h cross square by 2 mu into delta r square plus v of vector r into phi of r, which is equal to e of er into phi of r. So this is purely an equation containing only relative radial coordinate r. This is an equation for only radial coordinate. What is important in equation 10? This equation 10 contains the potential, okay, interaction potential between the two particles v of r. Similarly, we can write one more equation for center of mass coordinate, which will be equal to minus h cross square by 2m into delta rho square into phi of rho equals e rho phi into phi of rho. So this is equation purely depends on center of mass coordinate. Note that equation 12 do not contain any interaction potential, and for the same reason this will be discarded from further analysis. So equation 11 is sufficient to describe the particle motions in two particle system. Now what does this equation 11 represent? That's represent an equation similar to a single particle equation. So it's effectively speaking, it's an equivalent single particle system of reduced mass mu describing the motion in a central potential. So this particular thing can be shown in diagrammatically in this manner. Now what is this diagram tells? This tells the location of the first particle, this tells the location of the second particle, and this is the location of the center of mass of the two particles. Now when we write two particle system into equivalent single particle system, the two particles now is replaced by a single particle of mass mu, which is actually away from a relative coordinate vector r. Now this is purely a representation of a single particle system in center of mass system, center of mass frame of reference, which is shown in solid line. The dotted lines are actually a reference frame in lab frame. So vector rho is also shown, but that is not important for us actually for the analysis of motion. So vector r shown in the diagram is actually having the same magnitude and same direction as that was shown in previous plot. So vector r earlier was shown as the distance between two interaction particles. Now it has been shifted slightly towards the location of the center of mass. So this actually gives the complete picture of how we can reduce two particle system into single particle system. Now we can further reduce that particular equation. So in case of central potential, then potential will be function of only radial coordinate. So relative radial coordinate r is important for that. Now in such a case, we can separate the coordinates, angular part separately and radial coordinate separately, and only radial part of wave function is important. So we can write the equation 11 as d square of r divided by dr square plus d2 by r into dr by dr plus 2 mu by h cross square into e minus v of r minus L into L plus 1 h cross square by 2 mu r square into r of r equals 0. So that L into L plus 1 h cross square by 2 mu r square term arises because of the separation of the angular part from the radial part equation in the total wave function. So in this expression, L is angular momentum quantum number. Now in general, when we solve problem, in many cases it happens that a radial coordinate may not be 0 when the radial r coordinate r itself is 0. So but for solving problems, we require in many cases that radial wave function to go to 0 when r tends to 0. To achieve this modified radial wave function, u is defined. U equals r into capital R of r, or you can express that in terms of r of r only. So take the double derivative of this above function, you get this result 1 by r into d square u by dr square, which is equal to 2 by r into dr by dr plus d square r by dr square. The right hand side is the two terms contained in the previous Schrodinger equation, and that can be replaced by left hand side 1 by r into d square u by dr square. And again using u of r equals r into r plus r, that expression. So the Schrodinger equation now can be expressed as in terms of modified radial wave function u of r as d square u of r into dr square plus 2 mu by h cross square into e minus v of r minus L into L plus 1 h cross square by 2 mu r square into u of r equals 0. Or this can be written in more compact form, u double dot plus 2 mu by h cross square into e minus v of r minus L into L plus 1 h cross square by 2 mu r square into u equals 0. So in this expression, u double dot represent d square u by dr square. Do not get confused that with respect to time derivative. This is derivative with respect to coordinate r. So this equation is very simple form, and simple form applicable in spherical coordinates, and most probably it will be using only modified radial wave function. So this equation will be used for all further analysis. So that ends the lecture. Thank you.